Okay, great. Thanks a lot for the introduction. So, as you can imagine from the number of authors on this paper, it was a collaborative project. And this was actually a global collaboration between 3 groups within Autodesk and the Institute for Computational Design at the University of Stuttgart. And our group, the User Interface Research Group at Autodesk Research, was focused on the user experience side of this project that I'll be talking about today. But sort of step back for a second, there's been a lot of work in the HCI literature on interactive techniques for digital fabrication. But not so much of this work has looked at fabricating larger scale structures. So there's been some work on large scale 3D printing using concrete or steel. But these systems, they're only just emerging, and they're currently pretty limited. And so in this work, we kind of wanted to explore an alternative model for digital fabrication at large scales that we call crowdsourced fabrication. And the idea here is to use digital mechanisms to guide a large number of volunteers or other workers to build structures. So typically, whereas crowdsourcing typically involves creating a digital system that integrates in the sort of unique cognitive and creative abilities of human workers, here we're looking at integrating in their unique physical skills and abilities. And so this work can kind of be seen on building on 2 areas. First is large-scale, recent work on large-scale fabrication, such as the Prototyper system or Yoshida et al.'s work on human-assisted additive manufacturing. And on the other hand, on work that guides volunteers in performing physical tasks, such as the haptic torque system or the torque deck system that was presented at last year's UIST conference. And our contribution to this area is the Hive Pavilion project. So this was a 12-foot tall pavilion structure constructed out of 224 unique modules. And each of these modules was built through a collaboration between a volunteer worker and a 6-axis robot arm. And the volunteer workers, they didn't have any specialized training. They were just attendees of the Autodesk University Design Conference where we put on this exhibit. So here's a video of the Hive structure being built. You can see it being constructed there in the middle. And just as a brief overview, volunteers were given an Apple Watch to wear that provided just-in-time location-aware instructions. And the volunteer was directed to collect 3 bamboo sticks and bring them to one of 4 robot stations. And then the robot would kind of move into position, and the volunteer would load these sticks onto the arm. And then once been loaded on there and secured, they would tie a string to the bottom of one of the sticks. And then the robot would wind string around all of these sticks to form one of these modules. So you can see the winding procedure going on here. I think, yeah, you can see a completed module back there. And so then once the winding was complete, the volunteer would retrieve the module off of the robot arm and then bring it over to the pavilion structure, which was in the center of the build space, and then attach it on there. So I've given this brief overview of what the volunteers did, but now I kind of want to step back and talk about how we created an intelligent workspace to guide them in performing these tasks. So to guide our design, we adopted a set of 5 design principles: just-in-time learning and guidance, use unobtrusive technology, ensure worker safety, that's important, improve coordination and efficiency, and then active analytics. So first, we wanted workers to be able to start the task immediately with no training, and then receive ongoing guidance throughout the process. The main way that we did this was through a custom smartwatch app. So when the worker started, they would put on the watch, and then they were told that that would be their personal assistant through the process, not a person, but the watch. So here's some other examples of instructions that were given on the watch. And the watch also fit with this principle of unobtrusive technology because it leaves the hands free to perform physical tasks. And then to enable the watch to provide contextual instructions, there were wireless iBeacon devices that were embedded throughout the workspace. So the watch could detect when the worker had arrived at a particular station, and then that would advance the instructions. And then finally, we used wireless RGB LED modules like this guy here that were embedded in the stations and in the actual building materials for the pavilion. And there's some of these nodes in the audience, in envelopes, in like the sort of areas in front of your seats. So anybody's feel free to open them up and turn them on and try them out during the talk here. And so these modules could take on any color. And one of the main ways that we used them was to indicate the position and orientation for inserting a part into the structure. So the lights would take on a certain color, and that would indicate the how to you'd match up the colors of at the end of the sticks to insert a part. And to coordinate all of these guidance mechanisms, we developed what we called a foreman engine, a digital foreman engine that monitored the build process and then issued instructions to the workers and the robots. And one of the benefits of having this sort of digital system coordinating the build process is that you can do real-time analytics and visualization. So this was a dashboard display that was on a huge screen at the entrance to the exhibit, and it showed the progress on the build, which human workers were doing, what stage they were in the process, and then what the robot workers were up to as well. So this was kind of allowed people to monitor the build, but also it's kind of a motivation for people to take part. So I've described the guidance mechanisms. Now I kind of want to go back through the worker experience in a little bit more detail. So the first instruction given was to go to a training station. So a wireless LED at a station would blink in a color matching the band of the worker's watch. And this kind of set up a pattern that we reused throughout the experience, where a color matching their watch band would indicate that they would go to a particular location. So next they were guided to a stick depot and instructed to collect 3 bamboo sticks with particular color-coded end caps. All right. And then they were guided to take those to one of the available robot stations. And then first they were instructed to adjust an end effector on the robot arm. So there was a set screw that had to be loosened. They were to adjust an angle on that, and then tighten it again. And then load the 3 sticks onto the arm. And so you can see one of the LED modules here on the base of the station here, and that's indicating what orientation, what side of the stick to put down when you're putting it on here. And then for each stick it would be tightened, and then they would step back, and they'd have to confirm that they were behind a line. This is for safety. And then the robot would move into position to accept the next stick. So after they had loaded all the 3 sticks, they would be instructed to tie a thread to the bottom of the sticks and then initiate this winding procedure, which I showed earlier. So it starts winding. And while the robot was winding, the worker was guided to collect some of these connector nodes, which some of you guys have right now, that they would later attach to the pavilions. So you see the 2 of them were highlighted in green to say these are the ones to collect. And then they went back to the robot station, and they removed the completed part. First you had to unlatch a bunch of things here, and then carefully remove the part. And then they took it over to the pavilion structure, where you've got the 2 green lights you can see there indicating that this is the position to place the part. And then once they'd confirmed that they had arrived, these would change into colors that would indicate the proper orientation for attaching the module. And then the module was actually attached by tightening zip ties that were already on the nodes. And then finally, they would attach those additional nodes that they had collected earlier to the bottom of the attached module. And so we designed this experience so that participants could complete the process on their own with just guidance from the watch. But because this was a large public exhibit, we had team members shadowing volunteers as they went through the process. So this was a really ambitious project with kind of about 1 million moving parts. How did it go? Well, here's a timeline of the exhibit with each of the short colored horizontal lines representing when a part was started and finished. And the blue parts there, the parts indicated by blue lines there, are those built by volunteers, and then the red ones are those that were built by the project staff. So you can see we did some building before the exhibit opened on the first day. That was to test the system and put the first ring and a few other modules in place. And then over the first day, volunteers completed the second and third rows of rings. On day 2, we have 2 gray areas there. And these were points where we had to shut down the exhibit temporarily. So the first was due to funny enough, a string-to-integer truncation bug, which caused some modules to be built with the wrong geometry. So you can see some people doing repairs there, and somebody recycling some of the parts in the foreground. And then the second shutdown was because we had some concerns about the stability of the structure. And this was in part because some of the zip ties weren't tightened enough by the volunteers. And I'll mention that again in a second. But the architects on our team looked at the structure and added some reinforcement. And then from that point forward, you see a lot of red because we were badging in from that point on. But we still had volunteers accompanying us throughout the period. We just took a bit more of a role in making sure that the zip ties and that were sufficiently tightened. And so finally, here's a time lapse of the final day. You see lots of running around, and you can kind of see the modules being added at the bottom there. And then every time a ring of modules was complete, there'd be a light show, and you can see at the very end all the lights going off because the structure was completed. So it was completed in the end successfully and on time. So next, I want to kind of step back and talk about some of our findings from this project. So on average, it took about 20 minutes for volunteers to build a part, and about 17 minutes when the researchers were building a part. And if you think about this is actually pretty impressive considering the volunteers were coming in cold, and we were really experts after we'd been doing it for a bit. And here you can see a timeline that's showing the average time to complete individual steps. Most of the steps took about 1 to 2 minutes to complete. But kind of an interesting thing that you can see here is that when there's repeated actions, the volunteers learned really quickly how to do the actions. So the time to load the first stick took about 70 seconds, but by the third they were down to about 40 seconds. So they really learned the steps quickly. And then to gain more feedback on the exhibit, we conducted interviews on site and an email survey after the event. And in general, we see a ton of really positive feedback. So people really enjoyed the experience. One participant said, the technology was incredible, the networking between the robot and the app to guide the user in the workspace was amazing. But more importantly than getting praise, we got a lot of good feedback that highlighted some of the ways that this sort of intelligent workspace could be used. So one participant said, in construction, I can see extreme potential for both tracking progress of tasks, accounting for labor, directing workers to daily tasks, and making installation of pre-manufactured components easier to understand. So this kind of speaks to a theme of supplementing the skills that workers already have. Another participant said, this could be used in remote locations to enable unskilled workers to construct dwellings, etc., without the need for a team of specialized or trained workers. So in contrast, this is kind of more about standing in and providing skills where they aren't otherwise available. So you can imagine this in disaster recovery scenarios or community building projects like those that are done by Habitat for Humanity. So participants really got this idea, and they were really excited about it. So I just want to end and wrap up by discussing some other insights that we gained into this area of crowdsourced fabrication. So first, despite some challenges, the project was a success, and we do really believe that this idea has potential. Second, sort of key lesson was that adapting to unforeseen circumstances is absolutely crucial in this setting. In the paper, we talk about some ideas for how this could be done. We had workers accompanied by guides, but you can imagine a system where somebody goes through, they learn the task really quickly, and then they become the guide for the next set of users. Another area along the same lines that I think would be interesting is adapting existing workflows from the crowdsourcing literature, things like find, fix, verify, to the physical domain. Third, the guidance mechanisms, they were valuable for the novice volunteers going through, but we also found that they were really useful for us as the experts. When we had those challenges where we had to rebuild parts of the structure, we chose to keep the system going and using the guidance because it was just really handy to have. And then finally, a really interesting question is how to generalize this approach to arbitrary tasks. So, for example, here's a picture of us the day before the event began, assembling the 224 nodes that were used in the pavilion. So with each of them, we had to put them together, and then overall, we had to thread 8 zip ties onto them, which overall made for about a little under 2,000 zip ties. Then we had to put in 500 batteries. And then we had to arrange them by address, test to make sure that everything was working. And then to conserve batteries, we had to go through, switch all the nodes off. And then we were worried that the batteries wouldn't last, so we had to take them all out, recharge them, and put them back in. So there's a ton of these tasks that individually aren't that complicated, but we had to do it for this building project. And you could imagine a generalizable approach would have some mechanism for flexibly bringing in these other elements and tasks into the build process. So with that, I want to end, and thank you very much.
All right, any questions for the speaker? There. And there. Okay, Patrick, go ahead.
So Patrick Bowditch, Hasse-Plattner Institute. I really love the talk. And I think you already went in this direction. So I love this idea of the disaster areas. And so what's like the lowest level grassroots, no-tech implementation of your system you can think of?
That's really interesting. I mean, maybe you could imagine it as like IKEA-style manuals dropped by planes or something like that. Can you get more low-tech than paper instructions? I can't think of anything more than that. Maybe taking the human element out of it, and or sort of structures that partially self-assemble, but then you have some sort of human instructions for doing that. It's a really interesting question.
Yeah, Michael Jones, Brigham Young University, right here. So I'm wondering what they were building, and then I'm wondering how you think the human experience would have changed if they knew what they were building in advance. So if you'd shown them a big picture of the whole thing, maybe they could have figured out, oh, now I see where my piece fits in, and that might have taken a lot of ambiguity out of the process for your crowd workers.
Yeah, I mean, I think that's really interesting. I think that, I mean, in this case, we had it very compartmentalized so that people were just kind of guided in the task that they needed to do to build and add a part. But, well, I guess two things. I mean, I think that adding that kind of global view that people could see, that could be a great motivator. And we explored with this a little bit. I didn't mention it, but we had a mobile app that went with the conference that they were attending. And if you had built a part, you could bring it up afterwards and see where your part was in the structure on the mobile app. So that's kind of this I guess that's not motivation beforehand, but it's kind of cool to be able to see it afterwards. But you could imagine that where your work fits in being a motivator for people to participate in the first place.
All right, let's thank Benjamin again for the great talk.
Thanks a lot.